So good morning everybody. Today lecture is on HVAC. It is continuation of previous lectures. So previous lecture we started HVAC system and you have seen there is one compressor, because normally it will be a vapor compression system, but there are other types of systems also there. So from compressors, hot vapor will go to condenser to one throttle valve or expansion valve. From expansion valve there will be evaporator. So from evaporator again the gas will be going to compressor. Okay, so fluid will be flowing like this. Okay, normally the refrigerant will be like R134A or different type of refrigerants. Later we'll discuss in details. Now this one, if you want to put in TS diagram, it will be like this. Initially you are compressing gas. After compression you are cooling down this refrigerant, then there will be throttling. So throttling process actually isenthalpic process. I'll be putting number also 1 2 3 4. After compression 1 2 3 4. Okay, so 2 to 3 is your your enthalpy constant, isenthalpic process, isenthalpic 2 to 3. There enthalpy is not changing, but entropy is changing, and it is irreversible process. Okay, so we have seen this 2 to 3 is your throttling process or expansion process. So condensed liquid, it will be passed through narrow channel, then evaporation will be happening. So evaporator will be inside your room or inside your refrigerator, and the condenser part will be outside your refrigerator. If you see any refrigerator system at your home also, or any air conditioning system, backside there will be on serpentine pipes. Normally it will be copper pipe, and it will be releasing lots of heat, and if you touch it, it will be temperature will be very high actually. So condenser will be releasing heat, so temperature is high and it will be releasing heat to atmosphere, and evaporator will take heat from your fruit, vegetable, meat, fish, whatever item you are putting inside refrigerator or inside from your room if you are using for air conditioning system. For same system, same mechanism will be used for your refrigerator or your condenser system. Okay, now 4 to 1 we are assuming this is isentropic process, so that's why this line is vertical. If it is not isentropic, then line will be deviated. For example, it may be like this, so it will be consuming more energy. 3 to 4 is isobaric or constant pressure process. 2 to 1 it is again constant pressure process, while 2 to 3 is your enthalpy constant but entropy changing and pressure also changing. Now I got some information from this Johnson Control website. So ammonia and carbon dioxide cascade refrigeration system they are using actually for fishing vessels. So later we'll discuss what is cascade refrigerator system. Cascade system is like you have one system refrigerator and you have two refrigerator system, like you have done for your nuclear power plant. I said like two system will be there for Brayton cycle. One cycle will be giving some power and the cycle will be giving power. Here refrigerator system also will have like one cycle will be reducing certain heat, then again another cycle will be there to reduce further heat. So that is normally used for your cryogenic application or very low temperature application. So this Johnson Control for marine systems, they are they have already ammonia and carbon dioxide based system. Ammonia also can be refrigerant, carbon dioxide also can be refrigerant, H2 also can be refrigerant, other than your freon and fluorine and chlorine based refrigerant systems. So carbon dioxide refrigerant, low temperature side it will be used. For example, if I have cascade system like this, one cycle, another cycle. So one cycle is like this, for example, then another cycle will be like this. Okay, I'm not drawing properly, so it should be normally it will be like this. It should not go so long, so it will be like this. So 1 2 3 4 P Q R S. So CO2 and NH3. Okay, so similar way you can design your refrigerator system. So it will be cascade system is two system or three systems or multiple systems will be there. So CO2 will be low temperature side. So low temperature side means this one will be CO2 and this one will be NH3. Okay, 25% higher freezing capacity. So as per the company document, they are saying yeah, freezing capacity is higher for same space if they are using. Okay, and if they are using only ammonia based system, it will be giving less amount of freezing. Okay, so to increase system performance, they will be doing so many different mechanisms they will be applying. One is that cascading system, and several other system will be there, we'll discuss later. So here we see the common refrigerant. Common refrigerant, for example, water also can be one refrigerant. Okay, it is low cost, non-toxic, so it is very popular in many cases. R134A also a very popular refrigerant. So these are called refrigerant. Refrigerant is a working fluid flowing from compressor, condenser, evaporator. That fluid is called refrigerant. Okay, in thermal power plant you used only water and you change heat from condenser, evaporator, not evaporator, you can say boiler, and in Rankine cycle case. But in this case we don't have boiler, you have evaporator. Okay, so water is, you should remember the name also, like R7, R means refrigerant. Okay, R means refrigerant, and 718 some nomenclature is there, so we'll discuss later. So R134A, R744, carbon dioxide also can be there, ammonia can be there, hydrochlorofluorocarbons, HCFCs also will have refrigeration properties, hydrocarbons like R600A. So several refrigerants are there. There are ample names are there, but we normally, for our case, will be studying only the common part. Okay, so you should remember the refrigerant name, that chemical, that refrigerant, the designation R144, 718, 744. Those things you should remember. Okay. So R744 carbon dioxide, R764 SO2 sulfur dioxide also used as a refrigerant, R729 air, especially for aircraft engine they use air as a refrigerant. So desirable properties of ideal refrigerant. So thermodynamic low boiling point it should have. If it is a very high boiling point, then temperature requirement will be very high. So it should have very low boiling point, low freezing point also, high saturation temperature, high latent heat also should be there. Why latent heat will be there? When evaporation is happening, so small amount of fluid should take lots of heat. So it should have higher latent heat. Even condenser side also, if you have higher latent heat means the amount of energy it is absorbing to change phase from liquid to gas or gas to liquid. If amount of heat is higher, so it will be beneficial for us. Chemical, like non-toxicity should be there, non-flammable. If there is any leakage, let's say refrigerator you are using at home and flammability there, it can be dangerous. Normally we use it for kitchen also, right? So in kitchen, if some flammable gas is coming, so that may be very much dangerous. So non-corrosiveness must be there, non-irritating means health related point also should be there, and zero ozone depletion potential, zero global warming potential. We'll discuss later all these things, and short atmospheric lifetime. So quickly it should be depleted and it should be creating a separate molecule. If it is staying for longer time, that's also not good for your ozone depletion potential. Okay, so now see this refrigerant definitions. Global warming potential, or GWP, it is measurement of how much heat a greenhouse gas traps in the atmosphere over a specific period, usually 100 years, and it will be compared with respect to carbon dioxide. So carbon dioxide they will be saying 1 as greenhouse global warming potential. So this is baseline. So all other refrigerants should have more than that normally. Okay, ammonia will have 0. So non halocarbons refrigerant will have 0. For example, water is not having a greenhouse gas, so water will have 0 value. Okay, ODP, ozone depletion potential. So if some refrigerant is depleting ozone layer, so their potential will be some, there will be some values, and it will be compared with R11. Okay, R11 normally it will be 1. Okay, it's standard value, they will be saying 1. Okay, other refrigerant value will be like 0.01 to 1. Okay, so if I say R12, so then it will be like less than 1. Okay, so within that range the values will be there. Halons will be having CCl4 1.2, CH3 CCl3 1.11, so less than 1. So halogens will be more than 1. Okay, so here it is written R as a refrigerant, okay, followed by a dash line or some other points will be there. So those refrigerant name will be like this, R dash some number, so that will be refrigerant name. Okay, and normally the naming and ozone depletion potential, ODP or GWP, all these things will be decided by a ASHRAE. So ASHRAE website, if you go, they have all this criteria, naming of refrigerant, and lots of information will be there. So American Society of Heating and Refrigerating and Air Conditioning Engineers, so they'll be they're basically regulatory bodies, you can say. They'll be putting all the regulation digits and naming GWP potential, all the digits, it will be there in their website. They publish many books also. So if you want to know more about refrigerant and their effect, you should visit their website, ASHRAE. So naming of refrigerant are already told that it is a refrigerant, followed by 2 or 3 digits. The methane, ethane, propane series like X number of carbon atom minus 1. So X equals 0, CH4. Okay. So but 0 is ignored. So R12 and R22, it is having 1 carbon atom. Okay. So it should be R012. So similarly, other naming also you should just you go through it. So maybe some question I can give based on this naming structure. Refrigerant regulations. So if you see a refrigeration system started long back, and 1930s around, it was R12. It is having very high ODP, ozone depletion potential, like 10,000 they have written. Okay, so 1950, 1900, 2025, you see this ozone depletion potential gradually going down. Okay, so they have target like 2024 or 25 onwards, there will be no ozone depletion. Okay, greenhouse global warming potential also will be lower than 700. Okay, and this will be coming under again ASHRAE's classification A to L. So they have one document 34 specification. So there they have specified all this greenhouse potential and ozone depletion potential like GWP and ODP in their document. So which refrigerant will have higher potential, which have lower potential, it is there in their document. Okay, so A to L, you see this one, mild flammability, low toxicity, low GWP, hydrofluorine, HFO blends, safer than ammonia. Ammonia actually toxic in atmosphere. HC hydrocarbon based refrigerant, energy efficient than R410A and transcritical carbon dioxide system. HFOs replaces older HCFCs, lower GWP potential. So this ASHRAE A to L recommendation shows the list of refrigerant which you can people will be using. Actually the companies, especially the big companies, normally they will be using this latest refrigerant, and they are doing lots of research also, like many big companies for marine applications or domestic applications in land use. They are developing new type of refrigerant, new type of technology. If you see any refrigeration system, fridge or air conditioning system, every 10-15 years their technology is changing actually, because they want to increase efficiency. They are making more energy efficient, they are making less noisy, and they are working on the pump side, they are working on this refrigerant, they are trying to develop new type of mixed type or single compound or mixed compound they are using, and they are trying to develop new systems or new series of air conditioner or refrigerator systems. So A2L, this example they have given R32 and R54B. So there will be many others also. So many company will have their own company name also, and they will be putting some extra chemical to improve certain properties. So we have seen air conditioner type, like where air conditioner will be split air conditioner, window air conditioner, centralized air conditioner. So different types are there. So refrigeration type also like similar way we can divide, but there will not be any split air conditioner sort of thing, but technology I'll explain. So vapor compression system I already explained, like one compressor is there, then condenser is here, then one throttle valve is here. Throttle valve normally we specify like this. Okay, this is throttling. This is you are creating restriction. Okay, so whenever you are drawing throttle valve, just put this symbol. It will be looking good. Not this one, like this. Okay, then it will be going to evaporator, then it is going to condenser. So this is your simple vapor compression refrigeration system, vapor compression refrigeration system, VCRS. And absorption system, another system is called vapor absorption system. So there we can use water also as a refrigerant. Okay, how the system looks like? So it will have evaporator system. Okay, so refrigerant will go to one absorber, then there will be one throttle valve. Okay, from here it is coming evaporator, absorber, absorber to it will be going to generator, and there will be one pump. Okay, so what will happen, this evaporate, let's say water is there, water will be absorbed by certain fluid, or ammonia will be absorbed by water. Okay, so let's say liquid ammonia we have, or gas ammonia you have, and if you have water, so water will be absorbing lots of ammonia, or water will be absorbed in some lithium bromide solution very high rate. So when it is absorbing, it will create low pressure. Actually when it is creating low pressure, so that low pressure will be evaporating more the refrigerant. When it is evaporating, again it will take heat, so you are creating indirect evaporation. In vapor compression system, you create low pressure, then you compressed, you expanded, but here also you are doing same thing. So here will condenser will be there. So this part actually it is mimicking your vapor compression system, your compressor. Okay, it is mimicking compressor, but this part will be same. This is condenser. Okay, this will be releasing heat, then throttle valve, then evaporator will be there. Okay, so in this case H2O can be your refrigerant, ammonia can be your refrigerant. Okay, so basically these are common refrigerant used for vapor absorption system. Normally this will be used for your, there's a cold storage or similar sort of where high heat requirement is there, and big these will be heavy and bulky, so that's why you cannot use for your small room application. Okay, because you will have some extra mechanism, absorber, pump, generator, then condenser. But if you have window air conditioner, you can see simple one windows air conditioner, this much of size will be there. So this one you can fit in your window, or you can have split air conditioner you can use for your household. And this one if you are from North India, you are very much familiar with this type of figure, right? Lots of sieve square will be there. Okay, and water will be splashed over it, so water soaked thing will be there, and one fan is here. Okay, here I think 4-bladed fan, this is axial type fan. Okay, this is axial fan, so actually it will be taking air will be entering here, then air will be going out from here, and it will be soaked with water. Okay, soaked. When you are soaking, what air is going through the soaked cotton or the sieve, so air will get lots of moisture. When air is getting lots of moisture, so actually temperature will be going down. Later we'll discuss psychrometrics, so there I'll explain how this temperature is going down. Okay, so when you are adding moisture in air, temperature will be going down and you are feeling comfortable, cool environment. Okay, and this will be working only in low humidity area, especially in North India. And South India, like say Kolkata, Chennai, this area we cannot use this type of thing because already humidity high. So this purpose of this desert cooler is to increase humidity, but if you have already high humidity, you cannot use. So that's why in Chennai hostels or other nowhere is there, but North India everywhere it will be very common also, and very cheap also. In roadside vendors also they'll be selling this type of desert cooler. Okay. So evaporative cooling or swarm cooling, so this is actually evaporative cooling. Okay, so lots of moisture will be there and moisture will be evaporated, and when it is evaporating it will take latent heat. Latent heat when it is taking, so temperature will be going down. Okay, that's why this is working. So temperature can be reduced by 15 to 30 degrees, very high temperature reduction based on your ambient temperature and your humidity. Let's say temperature is very high, humidity very low. So in that case, you add moisture, your temperature will be down at very high rate, moisture will be going up. So finally you will feel comfortable room. Okay. Thermoelectric refrigeration system, this is also there, but this is a very less use is there for especially electronic cooling you can use. Okay, so when we write about refrigeration, so like R11, it will be like R011 as per the formula. Then you can represent in chemical formula like this: C carbon, F fluorine, chlorine, chlorine, chlorine. Okay, so it will be CFCl3. Okay, trichloro monofluoromethane. That name also you should remember: trichloro chloro monofluoromethane. So R12, R22 if you want to write, then so R22 means 0 to 2. So 0 means carbon. In the previous slide you can remember, C will be 0 plus 1, then 22 means H 2 minus 1, and F as it is 2. So I can write like C1 0 plus 1, C1, H2 minus 1 is H1, fluorine 2, then remaining is chlorine. Okay, so this formula becomes CClF3. CHF F2Cl. Okay, so monochloro difluoromethane. I think you are very much familiar with these chemical names: monochloro difluoro. Okay, now R113. So the formula is that so 1 means carbon plus 1. C will be like 1 is here plus 1, and 1 is for hydrogen, so 1 minus 1, and 3 is for fluorine. Okay, so my carbon is 2 carbon will be there, 2 carbon. So this formula becomes like F means 3F will be there, F hydrogen, chlorine, chlorine, H. So chlorine number is not given, so remaining part will be chlorine. Okay, so C2F3Cl3, F what C2 C F will be 3, F will be 3, then 1 2, where is H? Because there is no H, so there will be F, then C F3 Cl3 Cl. Okay, so this will be a formula for R113. So if I give R113, so you can decode actually, or if I give C2F3Cl3, then you should be able to write the name of refrigerant. Okay, thank you very much for today's lecture. Next class we will start the formulation of refrigeration system in HS diagram. Thank you.